Hello, my name is Luke Shravan. I'm a master's student at UT Austin, and I'm going to be presenting on behalf of my project team. We're investigating voice and dialect conversion for in low resource settings, and specifically we look at Japanese dialects. So the team is Bingma, Anchan Mohan, myself, Zingling Yu, and Eden Magari, and our mentor was Shravan Bansal. So just a word about the project motivation, objective, and social impact. I'll start by saying that a great majority of major language subdialects are underrepresented with very small amounts of labeled or parallel data available. And so that means that limited speech technology solutions are available to the people who speak these dialects, live in these communities. For example, in Japan, there's one major language spoken and 16 related low-resource dialects. And in India, there are 22 major languages with 700 low-resource dialects. So we looked at two specific things. One is voice conversion, so speaker to speaker within a low-resource dialect. Insofar as VC is useful for various kinds of multimedia applications, we believe that this can accelerate technology progress for low-resource dialect areas and communities. And the second thing we considered was dialect conversion. So this is actually converting speaker to speaker between dialects. And at a high level, our motivation for this was the idea that converting between dialects could improve communication and inclusion for people who speak low-resource languages. Aside from having potential great social implications, this is also an interesting scientific problem. So interdialect conversion, we believe, occupies kind of a unique space as a hybrid task of both translation and voice and or accent conversion simultaneously. A system that's going to be successful in accomplishing this task must be sensitive to various aspects of the speech signal, including prosody, accent, linguistic content, among others. And then lastly, actually designing a system architecture and training objectives to accomplish the task implicitly asks the designer the extent to which different aspects of the speech signal are separable, and challenges one to design architectures that are capable of actually separating the signal in such a way. So now into the actual experiments. We used two data sets. The first data set is the JSUT standard Japanese dialect. This is what people speak in big cities like Tokyo, for example. This is what we consider our high resource data set. And then we fine-tune our models on a small data set of dialectal Japanese that's composed of 5 regional dialects. This contains so 5 speakers for each dialect, each speaker speaking 100 different utterances. Here we describe the basic framework. So many will be familiar with this. There's 3 stages. The first 2 stages compose what's called the pre-training phase, and the third stage is a fine-tuning phase. So in the pre-training phase, we apply first a text-to-speech task to pre-train a decoder model, freeze the decoder, and then train an autoencoder-encoder by replacing the text input with speech, and then freeze the autoencoder-encoder in the last stage, which is the fine-tuning stage, for either voice conversion or dialectal conversion. So we have a couple examples. I'm going to start with this because I think the other one's broken. So this is one-to-one, one speaker to one speaker, interdialect conversion. This is the source speech.
中となると帰って食べてみたくなるとよね。
Target speech.
ないとなると帰って食べてみたくなるんだよね。
And this is the converted.
中となると帰って食べてみたくなるとよね。
We also have another conversion here that was using a different vocoder model. You'll hear this is much lower quality, but I'll share it just for completeness.
中となると書いててみたくなるだろうね。
We attempted then to extend the system to an any-to-any style interdialect conversion. And basically the way that we did this was by introducing a speaker-specific X vector that was concatenated with the encoded features. So this is the source.
中となると帰って食べてみたくなるとよね。
Target.
ないとなると帰って食べてみたくなるんだよね。
And then this is decoded.
中となる帰って食べてみたくなるね。
You'll notice that a lot of the linguistic content is lost, but the speaker-specific information, the tone and accent is preserved. So about 10 seconds. A quick comparison to other solutions that have worked on this. The majority of other works that we found relied on large amounts of data to achieve their objective, which would mean that they aren't applicable in a low resource setting. So what we think is unique about our work is the application of this kind of pre-training on a high resource language and then fine-tuning to achieve, apparently actually very good qualitative results. In conclusion, we believe voice and dialect conversion can facilitate technological advancement and inclusion for low resource dialect speaking communities. We developed a seek-to-seek style voice and dialect conversion system for low-resource Japanese dialects. Our results are unique insofar as that they accomplish this task in a very low-resource setting and bootstrapped with high-resource pre-training. And we believe there's several opportunities for future work. One would be a more rigorous evaluation of voice conversion, more rigorous quantitative evaluation, and the development of a plausible baseline model for small dialectal corpora. And then as well, the investigation of purely self-supervised representations and foundation models as an initialization for low resource VC and dialect conversion systems. So happy to take any questions. Thanks. Yeah. This one.
Yeah. So it's not time synchronous. There's not a frame-to-frame mapping this, right?
So in the, I believe there is in the fine-tuning phase.
Okay.
Okay. So I think we have usually only time for one or two questions. So.
Do you have any other questions?
Yeah. Okay.
Athena has a question.
Okay.
So how were the results evaluated?
Yeah, so I mean, so far the only evaluation we've really done is qualitative. So we're just listening to the examples. And I think this is, not being incredibly familiar with this space, what we found is that reading a lot of literature, people would report some quantitative metrics, but most of the people would just publish qualitative results online, and that was sort of the evidence of how good their system was. So that's why we made a note to say, I think there's going to be value in finding, more reliable quantitative evaluation techniques.
Okay.
Okay, thanks.
Good evening to everyone present here. My name is Sachi and my teammate is my teammate Aditya. We both are undergraduate students at Vishwakarma Institute of Information Technology in India. So our topic is automatic detection of fluency disorder in children. So the goal of this project is to reach out to the common population, like the local population, which doesn't have much access to medical aid, and to give them the medical aid that is required for helping them speak fluently. So the first phase will be to detect stammering and stuttering at the early age. And once it is detected, we can send out for the medical aid that is required. So the final goal is, as it is, to develop a system which will automatically detect the fluency disorder, mainly that is with respect to stuttering. So a few papers. This is the literature review that we have. So Shakil has presented a detailed review of speech disorder and the importance of acoustic features, machine learning methods, challenges, and future directions. Then Colin had elaborated the various characteristics of the stutter speech and SEP28K dataset for speech disorder. So what is the relevance of the literature to our approach? So the acoustic characterization and importance is very relevant because of our two-stage approach, and which would take into account the characteristics such as speech rate, stop-gap duration, BC, transition duration, frication duration, VOT, vowel duration, formants, signal energy level, etc. So we will be explaining a few of the stuttering in this slide. So how is the performance evaluated? So there are different stuttering levels. So first there's block, that is when people speak, when they stutter, there are gasps of air in between two words, or there's a pause. So those are like called blocks. Then there is prolongation, when they speak a particular word, a particular syllable is elongated more than the usual time. And there is sound repetition, which is the same syllable is repeated a multiple number of times. Then there is word phrase repetition, that is 2-3 words are uh, they are repeated consecutively. Then there is interjection, that is there are filler words that we use like uh, so these are some of the interjections. Then is our approach. So Mr. Shrikant Joshi will be speaking about our approach.
Hello, am I audible?
Yeah, we can hear you.
Yes, yes. So basically, our approach is with a two-stage approach. And here, for the demonstration purpose, for initial experimentation, what we use is acoustic modeling, which is used timid data set for acoustic modeling. We consider English as a language. And the models, which are 22 class models, which are trained using timid data. So these 22 classes includes basically all the vowels, 11 vowels, 6 diphthongs, semi-vowel, nasal, obstruents, all these silences and voice bar. These 22 classes includes. Once these models are trained, these are the American English models. So for the Indian scenario, what we are doing is we adapt the models or fine-tune the models using general Indian English database that we recorded of 20 speakers data, which timid prompts, sentence prompts are recorded using Indian English speakers. So around 500 sentences, timid sentences for the fine tuning purpose, and around 160 sentences for the evaluation purpose. So this includes 12 speakers for the fine tuning and 8 speakers for the evaluation purpose. So once these models are trained, so we can use these models for stuttering and stammering purpose. Here, basically what we are emphasizing on the methodology basically. We're not collected the data for the children, but what is the adult data that we have, we are using for that. So two-stage approach consists of first stage is speech segmentation. So using this trained acoustic models, we can segment the data in terms of these 22 classes. Once we get these 22 classes, further evaluation about the performance like blocks, prolongation, interjection, sound repetition can be performed on the segmental level. So the feature that included in the presented on the previous slides, we are using the segmented data for the second stage. The orthographic transcription, that is the speaker under test, which is used for the read sentences, right? So what he is doing is he is reading the prompts and the orthographic transcription of that prompt which is available. So that is a reference and the segmented data which is used for the evaluation purpose. So Sachi, you can continue.
So the data set that we implemented, so we used the DARPA Timid Acoustic Phonetic Continuous Speech Corpus for training. So it has, there are like 8 speakers in the training phase, also in the testing. Okay, so that is the data set that we used, and we used GMM HMM modeling for the purpose. Using HTK, we had used at Kali, but in the backend we had also tried with HTK. So the result was 22 class phoneme had a correct recognition of 50%, and with adaptation it had 73%. So some of the challenges that we faced are as like it's considering Indian scenario with several regional languages. So it is important to implement the ASR system, which should take into account a particular region. And then there are like majority of the remote population uses regional languages, and detection of stuttering at early age should include L1 only, that is the language. So these are some of the references. And yes, that is it from the end of our presentation.
Questions from the judges?
I just have a quick clarification. How do you account for the noise? Because you have the language and the different speech issues.
The noise.
Yeah.
Question, I could not hear question properly.
Can you repeat the question?
Yeah, so I was just wondering, how do you account for the differences? You know, I call them noise, but it's, you know, like between, you have different languages and different speech issues, right? The prolongations and so on and so forth. So how do you distinguish everything in?
Yes. Sachin, can you go for the previous slide, that approach, our approach? Previous. Yes, yes. So basically what is happening is here it's a two-stage approach, and in two-stage approach, the first is segmentation. First part is segmentation. So the speaker who is a problem of stuttering, what he will do, he will read aloud a particular sentence, sentence or prompt we can say. Then the segmentation block will give the phone level or 22 class level segmentation. So once we get this segmentation, then we can evaluate based on those segments. So we know the orthographic transcription, and based on the previously explained parameters. So just can you go for the previous slide, Sachi? Previous. One slide back. Okay. So the segments. So next. Next slide. Yes. So approach is.
There's a delay problem.
So we are on the performance evaluation slide.
Back one slide back up. One slide. Okay. So here, once we have the segments which are present, so stop gap duration or vowel to consonant transition. So many times what happens is this duration, this transition takes more time. So this we can record a transition once we have the segments. So we know the general how much time it is taking for the normal speaker, and how much time it is the stutter people those are taking. So the time duration or the frication duration or a voice vowel onset time. So all these things can be evaluated based on the segments which are available to us. So right now we have not processed all these second stage, but this is our hypothesis that based on these particular parameters, we can evaluate the performance of the different like prolongation or blocks or repetition. All these things can be evaluated. So this is we have to implement a second stage basically, but the once we have the segmented data, it is very means convenient to implement this second stage. So important block here is the first stage, that is segments, how we get the segment with better accuracy. And for that we use the technique which is training HMM and adaptation or fine tuning with the Indian English data. So that's what we used over here. The languages we are not taking into account at this point. We don't have the data of the different languages, Indian English, Indian languages. Data set is a problem.
Yeah, sorry. Are you happy with?
Yeah.
Okay. I think we got the answers. Thank you very much. Let's take again.
Hi, thanks.
Let's see a little bit some.
And my topic is German lip reading system. My name is Zheng Yang. I'm a PhD student from Technical University of Braunschweig. And my teammates is Thomas Kapp and Matthias Dunkelberg. Okay, then what is lip reading? Because normally we use speech recognition to based on acoustic information, and the lip reading use the visual information, use the movement of our lips or the movement of the face to recognize the speech. And the target is same as the acoustic speech recognition. Is also text. And lip reading can be used in many applications. For example, to transcribing the silent films, and also helping people suffer from aphonia, and also support crime investigation. For example, in the World Cup, I think, yeah, for the World Cup, maybe the lip reading can also be used to detect what people have said. And so it's the reason why Martinez always masks his mouth to message. Okay, and our method is transfer learning, because for German, the acoustic information has a lot. We have a lot of German acoustic data, but we don't have a lot of the labeled German audiovisual data. And one reason is that the transcription of video has less than the acoustic information. The second reason is that the privacy, because the face information of the is very important to humans, so it's also one reason. And our method is transfer learning. It's so compared to German in English, we have more data, and these two languages are acoustically very similar. It's the reason why we can use transfer learning. What does it mean? We use the pre-trained audio-visual hidden unit word model, and it's pre-trained on unlabeled audio-visual English data. And for the target model and data, it's a German. Here is a lip reading, and trained on the labeled German data. What data that we use for the source data is English, that we use the lip reading sentence and box style. And for the target data, we use the smartphone from the University of Munich. And it has 30 hours. It's much less if we compare the amount of data to the English. The only 30 hours, and for English we have almost 2,400 hours. And our results. Basically, I finished this work in these 2 days, and so the model is still training on our class. But we can see the word error rate it's not reached, is 68%. It's not so good. For English, normally we already have 20% word error rate, only with the lip information. And we also have a demonstrator that I can show now. Here we have the face tracking and also the extraction of the regional images. Furthermore, we also have the lip reading with support lip reading and the audiovisual speech recognition. Now I can share my stop sharing.
Don't forget to share it on Zoom, okay?
So as you can see, I'm in the screen, and I can zoom in, zoom out, also change the frame rate. For the landmark visualization, because we need a robust audio visual ASRV, I can little bit further, and maybe I can move to the camera. And the map is the landmarks are detected successfully. The information of the video into the neural network is transformed, and it's all automatic. It's always centered in the center of this camera, so that the neural network has a better input. Currently, it's because the German audio lip reading is still training, and what I can show is English lip reading and English audio visual. Maybe I later I speak in silence, and you will not hear what I have said, but then we can. What I will say is I'm happy to be here, and let's see what the models can recognize. Sorry, it doesn't work. Oh, okay. Yeah, I know the reason. Yeah, as you can see, the frame rate is 5. Actually, I need to set it to 25. It's a rate. Now it definitely works. Pay me to be here. Only pay me to be here. Yeah. And the second one is I'm happy to be here. And as you can see, it's only based on this rate. It uses only the visual information. And basically, there's no acoustic information. And if I have the, for example, when I'm speaking and you can talking when we sit in a cafe or in a restaurant, there's a lot of noise, and then the audio-visual ASR will have a better performance. If you want to have a try, you can come to me, and afterwards, then yeah, that's my presentation. Thank you. Questions?
Just to understand, so your system is trained for German?
Yeah, my system is trained for German.
But you...
Yeah, currently the model, as you can see in the last slide, currently the model is still trained on cluster. So basically, I finished my work in these 2 days, and it's a race. Yeah, but tomorrow I will get it. Thank you.
Yeah. But you're not a German native speaker, right?
No, I'm not. But I finished my master study in German, and currently I'm also a PhD student in German.
So you trained the system based on Chinese speaking German? Or?
No. In the data set, it's from the University of Munich, and it's a native speaker.
I have a question.
Yes.
Do you speak German?
Yes, maybe I can talk with Thomas in German, actually.
Yeah, his German is pretty good.
Okay, cool.
Yeah, thank you.
Thank you.
Thank you. Hello, I'm Chihiro Taguchi. I'm presenting this slide from the United States. I'm a PhD student at the University of Notre Dame. Today, I'm going to present our project about building a multilingual speech-to-IPA system. Next slide, please. Thank you. Why speech-to-IPA? So the first problem is that the transcription is a very time-consuming process in language documentation. And also ASR for IPA is understudied and underdeveloped when compared to other techniques like orthography transcription. So the solution here is very simple. We need to build a speech-to-IPA model which can be applied to any languages. And the most significant social impact of this task is that it can facilitate language documentation process for endangered languages. Next slide, please. So, but here's the problem. Overall, there are few high-quality speech-to-IPA data set out there. So we need to do some workaround. One possible workaround is to do orthography to IPA, which is also known as G2P. And for this, we used Common Voice dataset. We could use off-the-shelf modules for G2P task, but they're often not very accurate. Additionally, we also prepared manually prepared rules, and it's restricted to only spelled as pronounced languages. So it excludes languages like English because it contains many irregular spellings. Also, we created dataset manually from Forvo, which is somewhat similar to Common Voice, but it's basically word-based. And we manually annotated phonetic transcription for Forvo data. Next slide, please. Thank you. So here's our initial ideal goal. So we wanted to include these languages, these data set, so that it can cover geographically diverse and linguistically diverse and phonetically diverse languages, and fine-tune these data sets on a pre-trained model from Wave to VEC for CTC. Next slide, please. If we follow this scenario, we could cover these phonemes. Basically, the phonemes with asterisk mean that they are very uncommon across languages. So if you look at this, you can see that our model would cover most of the common phonemes that appear in most of the languages. Next slide, please. These are some rare consonants from non-Pulmonic. Next slide, please. And these are vowels we could cover. Next slide, please. So, but our experiment failed right before the deploy. So we used our older model with trained with only on Common Voice, which included Japanese, Polish, Maltese, Hungarian. It's obviously less diverse, linguistically diverse. But as we will see, it worked somehow. Next slide, please. So here is an example from the results. Obviously, based on trained on Japanese, Polish, Maltese, and Hungarian. So the testing on Japanese would be not very surprising. Here, maybe you can follow the predicted output. I will pronounce the sentence in Japanese. 森永の美味しい牛乳は濃い青色に牛乳瓶をあしらったデザインのパック牛乳である。I think you could say that the prediction is not very bad when compared to how it's actually pronounced, but the character error rate shows that it's 23% wrong. And is it good or bad? Next slide, please. So we need to think about new metric that includes phonetic similarity. It's basically Levenshtein distance with phonetic features. We dubbed it as phone distance, PhD. Sounds cool. So it's basically vectors of features, phonetic features. And we averaged it over the length of the reference sentence. And we get feature-based phoneme error rate. And based on this, even though character error rate is 23% for the example above, it would be like 12% error rate. Next slide, please. And I want to do some short demo. It's from Karabakh Armenian, from with the same model we use for Japanese. Can you play the audio, please?
Երկու աղբեր են ինում, մինը խելունգ են մինն էլ դոնգի։ Խելունգ աղբերը միշտ են դոնգլեն պինիցնումա ու չրչարում։ Ենքանա չրչարում, վեր դոնգին հույսը կտրումա։ Մին օր էլ երակենում թա։
So which looks better? I think prediction by our model is not so bad, but it's just in terms of character error rate, it looks bad. Can you move on? So in terms of character error rate, it would be very bad. But for a feature-based phoneme error rate, it would be like somewhat better. Next slide, please. So here are our takeaways. So we built a new speech-to-IPA model. It's low resource, but it works somewhat better. And it enables faster language documentation. And we also proposed a new metric for IPA generation. Well, we have lots of future work to do, but here's our progress. Thank you very much.
So if you have questions, please use the microphone. Because yeah. Should be on.
I have a question. Have you considered starting from a really large multilingual recognizer, like for example, OpenAI Whisper, and just adapt it to your task? You know, use the small corpora you have to adapt something like Whisper to produce IPA symbols.
I didn't try Whisper, but I believe that Wave2Vec pre-trained model is also multilingual. It was trained on like more than 50 languages. So in terms of that sense, I think it can adapt to many languages.
I'm just wondering, you have Maltese, and Maltese is a mixture of Arabic and Italian and English, all mixed together. How, does that impact the accuracy, or?
That's a really good question. So for Italian and Arabic words, it basically follows the orthography pronunciation. But when it comes to English words, it's English. So ideally, we needed to omit or exclude somehow those English words. But so far, we didn't do any manual, filtering or automatic language identification. We just fed them. So the data set, speech-to-IPA data set from us might include some errors because of that code switching. Good question. Thank you very much.
Okay, let's see again.
Hi everyone, my name is Abdel Mahmoudi from Tunisia. I'm a PhD student. I am presenting this work on behalf of my teammates, Mehmet Shawi and Hema Fluency. So probably, as most of you know, that even if the modern standard Arabic is the official language in the Arabic countries, it has very different dialects and subdialects. These dialects have similarities and differences. And on digital channels, Arabic speakers express themselves better in their own local dialects and by their own voices instead of textual comments. Therefore, it's important that we give to this community the chance to express themselves using their dialect. Once I attend a meeting, a virtual meeting on Zoom with some of my colleagues, and one of them said the word kashha. I was totally surprised because the word kashha in our dialect, in Tunisian dialect, is considered as a bad word. Then I understand that the word kashha in Saudi means you are pretty. And in our dialect, it means you are ugly. Also, when I scroll on TikTok and on Facebook, and when it comes to code switching speech, when I scroll on mute mode, I cannot really understand the subtitles and the captions of the audio due to the wrong transcription of the code switching of the frame language along with the Arabic words. So either the frame words are skipped or either they transcribe in the wrong way. How can I?
You want a request or accept?
Okay. Sorry?
Well, oh gosh. Okay, that probably will take too long. This is your audio, right?
Yeah.
I hope this works.
Yes, thank you. The goal of our
Someone, you have to tell someone to grant access. There's 4 emails now.
The goal of our model is to facilitate the speech interaction between Arab nations by recognizing the speaker's dialect, and it will be in the front of multiple applications, including ASR, machine translation, voice bots, and e-health applications. The impact of the ASDI model, it will help the disabled people like deaf and blind people and illiterate people to be included in the audio-visual experience, and it will enhance the customer services in banks, hotels, airports. It will overcome also the language barriers in higher situations such as a hospital and court. But also it will preserve the linguistic diversity and prevent the Arabic dialects from dying out. To do so, we build our ASDI dataset, since the Arabic dialect is considered as a low resource language, and there is not like a multiple public available dataset. And since dialects are not static and they vary across space and time, our dataset is up to date. And due to these changes, we need to consider the presence of the code switching in the speech, in the Arabic speech. So our datasets contain more than 30% of code switching audios. And we don't rely actually on automatic annotation. To build an accurate model, we prefer to annotate our data manually using by Arabic native speaker annotators. We hosted the podcast platform over the YouTube videos because of the quality, and we tried to diversify as much as possible the domain. We chose politics, entertainment, education, culture, and etc. Our total size is over than 250 hours, which are equally distributed over the 18 labels. And the dataset contains more than 900 speakers and more than 130 audios between 2 and 10 seconds, split into train and validation steps. For the ASDI system, during these 2 months, we managed to do the fine-tuning of an Arabic wave-to-wake 2.0 model on automatic speech recognition to better determine the context representation for the input audio. Our goal is to fine-tune the ASDI dataset using an already fine-tuned Arabic wave-to-wake model, and using first the noisy data and then using the clean data. But our ultimate goal is to retrain the first multidialectal acoustic model that is dedicated to Arabic dialect using the Common Voice public dataset and the ASDI 17 public dataset, and then fine-tune it on our ASDI for dialect identification for Arabic dialect using our ASDI dataset. Thank you so much.
There's time for questions.
Questions? So what is the technical novelty?
Actually, we focus on building a new dataset which considered as a great contribution to the state of the art. We can use it to enhance the language identifications and models that are present today. Thank you.
Okay. Yeah.
Okay.
Thank you. So this was the sixth presentation, right?
Assalamu alaikum. My name is Mansoor. I'm a researcher working on self-supervised transfer-learning ASR model for Sudanese Dialect. Okay, first, the Sudanese Dialect. Sudanese Dialect is a subcategory from Arabic dialects. We have Egyptian, we have Lebanese, we have Gulf dialects. The Sudanese dialects, it's unique for, it comes from like several kind of tongues, old languages, Nubian, Badawi, Egyptian, or Egyptian language. Like this picture, this is a wooden bed. It's called in Sudanese Angarib. There is no Arabic word for this this tool, and it's specific for Sudanese dialect. The Sudanese dialect also affected by Turkish word like the Turkish prefix tash during the colonization, tash like senior, mid-senior, like tash katib, senior clerk, and Hakim Basha, senior medical officer, and also affected by the Turkish suffix khan, which means base, Shafa Khana, dispensary, and ASDI Khana, pharmacy. All these words, like they are Turkish origin, but are used in Sudanese dialects. Also, the Arabic dialect, it's the main contributor in the Sudanese dialect. It's Arabic, but it's Sudanese. Like here, we have added some letters for Tawaha. Tawaha, this is the MSA version of Tawah. Tawah, this is the Sudanese version. Lawaha. Lawaha, this is the MSA version. In Sudanese, Lawlaha. This is the kind of differences even in Arabic language. Amalgamation, this is addition, and this is amalgamation. Amalgamation, we have bila shay. This is the MSA word. And in Sudanese, balash. Hadi sa'a, this is the MSA. In Sudanese, hassa. It's like affected by the way of Sudanese speaks. Even the Arabic language affected by the way of Sudanese and their way of speaking. Okay, we all know this card is Volkswagen Beetle. The linguists in Sudan, they say that we have a frog. Frog, this is the name of the car in Sudan. We call it frog, but not frog. Frog, this is the English word. We call it Garonja. This is Garonja, means frog. But till now, they don't know even what's Garonja came from. Is it African? Is it Arabic? Till now, they don't know. Okay, motivation. Usually, dialects, this is the way of like daily speaking for songs, for tales, movies, even drama. And it's not like MSA for formal speaking. The problem is that there is no speech data that's set for Sudanese dialect. And also, most of the Arabic dialect, NLP, and speech, they like classify Sudanese as Egyptian. There are a lot of difference between Sudanese and Egyptian, as I mentioned before, but they just classify them as they are what they. Okay. First, to make a speech recognition model, you have to have data. When we tackled this problem, we found that there is no data of Sudanese dialect, or there is no annotated data of Sudanese dialect. For that, we collected data from YouTube videos, SLT audios, and transcribed them as speaker said them. Maybe they said them wrong, but we transcribe them as they are. Then we built a data set consisting of 544 records. We have 3 females and 24 males. They are not distributed equally, but this is the way of like the data we collected consists of 4 hours. Okay, we trained one to rec 2 on Sudanese data sets. It's like heterogeneous data set, MSI 2.5 hours, and Sudanese dialect 4 hours. The results were during this hackathon were 74 error rate. This is the best result during this hackathon. We didn't use language model. We just like used a recipe from other researchers. We just feed the model the Sudanese data sets with the MSI data set, and we validate on just Sudanese data during this hackathon. Okay. Okay. Also, we have initiative called RAW in Sudanese, meaning you shout for help. This is an initiative website to collect more Sudanese data. We got Arabic dialect identification 17 dataset. We made a website around it to make people, to enable people to listen and write transcription for the Sudanese dialect. Also, there is updated version.
The updated version you have to reload.
This is the website. We have nearly 78 hours. We are now at 2 hours and a half. Right now we are 2 hours and a half. And we are doing the work. We are just volunteering, but we are doing the work. Also, we trained Whisper, OpenAI Whisper, during having case community event on the Sudanese dialect, same one as same data set. We got 56 word error rate on small one, medium 44, and large one 41.
Okay, thank you.
I have a question about Sudanese. How intelligible it is for standard Arabic? Like if a Sudanese person comes here and speaks, do you understand? Do people understand them at all or not? Because at the beginning it sounded like, wow, there are so many differences.
Yeah, there are a lot of differences. But there are some research on the closest dialect for the MSA, and they found that it's like number 2 on the chart. There is Omani, I think that, and then Sudanese.
Interesting. So because at first it sounded to me like, wow, this is like Morocco Arabic, which is supposed to be very difficult. So, but this closeness to MSA, maybe it makes things easier.
Yeah, but there are some specific things that you have to consider. There are some differences even the way of the speaking there. Like for us Sudanese, when we speak with other nationalities, they say that you speak very fast.
Okay. If you have no more questions, then we can move on. Okay, thank you again.
Hello everyone, 2022. Our team presents the topic of voice preserving speech machine translations. Our team consists of 4 members under the guidance of Amis Hunsen. Language barrier in spoken communications with locals is one of the major challenges that foreign tourists encounter when traveling to Vietnam. Vietnamese is a tonal language with 6 different tones that detect the meanings of the word, making it difficult for non-native speakers to quickly observe in a short amount of time, especially English speakers. We would like to propose a prototype of a cross-language voice translator application which allows English-speaking travelers to order food, ask for directions, and communicate with locals by tapping their phones. Local vendors can also benefit from our systems as they can provide the service to foreign tourists without having to deal with unwanted language barrier. Our system can enable non-Vietnamese speaking persons to speak Vietnamese with their own voice, and we aspire to demonstrate the system in form of a cross-language voice translator applications. The proposed system consists of 3 core modules, as illustrated below. RSR to transcribe English audio to corresponding text, English Vietnamese machine translations, and voice cloning by TTS, which can generate Vietnamese spoken audio using the original speaker voice. Our main contribution is voice cloning by text-to-speech models for Vietnamese, which incorporates the speaking-enabled embeddings of English input audio to synthesize Vietnamese spoken speech with the voice of original speakers. For the automated speech recognitions, we intend to use powerful last-written English way-to-way tool. For the English Vietnamese machine translations, the empty modules we use from Hugging Face equal empty text, multi-domain translations for Vietnamese English, which use a larger and better quality machine translation dataset. For local language speech synthesis, we base on FastBit2 models, which is popular model work well with low-resource language and easy to control speech characteristics like speed, tone, loudness, and timbre. To make voice cloning and preserve the character of the voice of the tourist who speak in English, we build a model multi-speaker speech synthesis based on FastBit2, then inject the speaker embedding of the English speaker to convert the voice output. Here is our demos. We have an Ask button here. The user can hold the button and then record. The output of the RSR models will be the input for the machine translations, and the output of the machine translation will be synthesized into the voice of the characteristics of the recorded voice. Welcome to the conference. Welcome to the conference. Chào mừng hội nghị. And here are some sample audio we have made available for you to try. On the left is the English voice, and on the right is the Vietnamese voice adjusted to match the input voice. In the long term, we envision develop a real-time system, then provide a high-performance API to handle multiple concurrent requests. And thanks for your listening. Thanks for the enthusiasm of our mentor, and thanks for the sponsoring of the organizer.
And why it scatters its bright beauty through the humid air. Và tại sao cái khí có tính chất đang bị tiết qua không khí hầm ấy?
So we have the persons online. If you have any questions.
Yes, I can answer your question.
Do you have any questions? We have the persons online. Yes, so the question that I was
Use my
as a system for high resource languages to preserve the speaker characteristics after the translation.
Can you repeat your question?
I was wondering if there is such a system for high resource languages. You presented it for Vietnamese.
Okay. Can you go to the slide of the to speak for Vietnamese? Go down. Yes. For the to speak for Vietnamese, we propose G2E, the graph from the graph from two IBIs, and we use it to make the Vietnamese text to speak, and we were training on the dataset of about a multi speaker with about 15 hours, and for the cloning, we propose the model that embed the speaker embedding for the text to speech so that it can clone the voice of the other speaker.
I have another question. What would you say is the biggest innovation in this project?
Can you go down with the next slide? Yes, you can see that the multi-speaker synthesis here is the first bit, and we custom it with the speaker encoders to extract the speaker characteristics, and we try to add it's called the style layer, the style layer norms to addition the feature for the text to speech to make the voice with the flavor characteristics of the input audio. So the main contribution here is the custom model which it can clone in.
Okay. Okay, so we can back the speaker again, and we can
Hello everyone, I'm Nina, and on behalf of my team, I'm presenting the work that we have done on detecting mispronunciation on Arabic language for non-native language learners. And our mentor is Dan Salvador. So basically, if I want to mention the goals and aims of this project, we all know that when you want to learn a new language, which is not your mother tongue, the most difficult part is pronunciation. And another part is that this pronunciation part in the classroom receives less attention because of like time-consuming, the quality of assessing the pronunciation most of the time is subjective. And another goal is also to support learning Arabic language and help non-native language learners for improving their pronunciation skills. And also check the wave-to-wave efficiency on training Arabic dataset or our Arabic dataset. So the social impact is also connected to the goals. Basically, it's help language teachers and also try to improve autonomous learning for new languages and also improving e-learning experience. So the description of the dataset that we have is 40 native speakers and 40 non-native speakers who learn Arabic as their second language. Their level of proficiencies are intermediate. They read 10 sentences, all of both groups, native and non-native speakers, and both groups were adult, and we checked the annotation, and we have the annotation on part of the data based on word and phoneme levels, and the labeling is based on ATR, which is common for Arabic transliteration. And but the biggest difference is what we use for our training. So we only got access to 10 speakers out of these 40 speakers. The 10 speakers got ready before the hackathon event, and it's almost 150 utterances in less than 30 minutes, around 90 minutes. So it's not big at all. It's too small. You will see the results, which is quite interesting. So the sentences are 10 sentences that took from Quran based on the purpose of the study, because the idea is that non-native speakers have specific problem in pronouncing some specific consonants like ain, which it doesn't appear to other languages. So they choose these 10 sentences and collected the data from both native speaker and non-native speaker. So this is the one sample of from non-native speakers, which they made errors in their pronunciation. It has annotated on 2 levels, sample, and the first line is the ATR system. I can play this, then you can hear.
Alhamdulillahi Rabbil Alamin Ar-Rahmanir Rahim.
And then the next example is without errors, basically.
Alhamdulillahi Rabbil Alamin Ar-Rahmanir Rahim.
You can guess that those consonants here are pronounced correctly and more. It was more vivid from the previous one. So we use word-to-word for our system. These are the lists, which it's not really important at this point. I just want to jump to the result. We got 100% word error rate for our system.
And then we decided to go to, instead of order array, go to check characters. And based on the character, we got 86% for evaluation, and for test set, it was like 90%. So we took samples. You see that for the predicted string, the model could only detect one phoneme correctly out of like 8, 9 phonemes on the original string. So our model basically couldn't work well, and there are some big issues for this really bad result. We think that the biggest challenge was the data was quite small, and we had almost 2 speakers in the test set, and the number of utterances were not that many that the model could distinguish properly. And then the transcription was quite different, and we didn't have time to mapping the character to the Arabic alphabet. So those are the things that we think if we work on them, the result will be different. And the biggest thing is this audio file has intonation and speech rate, which can affect the model. Those are the things that we are considering for further study. And thank you for listening to my presentation. Any question?
I have a comment. It seems to me that because you pick Quran sentences, people were kind of reciting, and that's not spontaneous speech. There's a bit of singing. So if you started from a pre-trained wave to back, maybe this is compounding your problem.
Yeah, that's what we also today we talked with mentors here, and then we reached this point. If we also transcribe our data to the Arabic transcription, then we can use the pre-trained Arabic models, and probably we will get a good result. Because now we only use our own model without pre-trained Arabic.
Yeah, but that is for sure. But I'm also pointing out that the nature of your data is kind of a very specific kind of way of speaking, right?
Yeah, that's true.
So I would definitely either that or ask the people to just read the sentences versus reciting them, right?
We basically have 2 data sets, but up to this hackathon only we got access to the part that people read through Quran, because we have a historical text as well.
I have a question about the matrix. Because mispronunciation assessments normally use the L1 score, and because mispronunciation is always in the phoneme level, as your data set has shown that it's also labeled in phoneme level. But why do you use word error rate to evaluate?
So we use that because we got access to the data quite late, and we start to work on the data without having the annotation of non-native speakers. So that's why we just use the whole sentence and work on that. But that's true, that if for the mispronunciation, you need to go to the smaller level. Yeah, but at the time that we started to work, the annotation of non-native speakers, we didn't have access to that.
And maybe one suggestion is that mispronunciation is always treated as a anomaly detection, and they normally train their model on clean data and only use the mispronunciation for assessment. Maybe you can also consider.
Yeah, that's a nice idea. We will check that. Okay. That's the second alarm.
Okay.
Thank you.
Okay, thank you.
Jonathan, can you open your microphone?
Can you hear me?
Yeah, now we can hear you.
Great.
So our team took on a challenging task of designing and evaluating the operation of the Yoruba dialect transcription system. To be mentored by Thomas. Next slide. Yeah, so Yoruba is the third most spoken language in Africa, and it's a tonal language. Yoruba orthography makes notable use of tonal diacritics and orthographic diacritics, and it's a language that is spoken by over 40 million native speakers. It's a very low resource language. That's quite a huge number of available labeled corpus. Now, so therefore, there are like applications like automatic speech recognition and machine translation models. So the goal of this hackathon outside was to develop a Yoruba dialogue transcription system that allows communication between systems and non-speakers. Next slide, please. Yeah, so as I've said, that our solution was to develop a Yoruba dialogue translation system, and this included three main parts. At the speech-to-text module, where we used word-to-vec, and the automatic damage restoration module, and then the machine translation model. So what we did in our solution was to deliver 4 Yoruba data sets that are available for speech, that constitute around 9 hours of transcribed data set, and then a menu 20K data set for building machine translation models that is available, that we contributed to the Hugging Face. So we're able to fine tune the multilingual models for both. Yeah, so in the next slide, I'll be showing you through our high-level framework. Please, next slide. Yeah, so this is just the high overview of our dialogue system. I'll have the audio and then the Yoruba STT model that generates transcript. So what we did was to build the error and diacritic restoration module. And with this, it was created an artificial data set where we make an error generator function which can insert, delete, and replace random characters in a sentence and remove diacritics. And so what we did with this artificial data set was to train our error and restoration model. And because what we did was to make sure that we find ways of correcting the errors in the speech-to-text model so that the empty model can give us sensible outputs for translation. So in general, this is what we worked on. Our main focus was on the error and diacritic restoration system because, as I've said, the diacritic has diacritic characters, so we had to find ways of working around this, and especially the error correction on the diacritic. Next slide. Yes, our results for the STT, we got results with a rate of 1.7%. And that's compared to the state of the art. Then our automatic diacritic restoration. With this, what we did when we generated the artificial data set, which we used to train the model, on the test set, we're able to reduce on the word error rate from 52% to 26.2% from the data set. Then, yeah, so these are like evaluation results for each of the components that make up the dialect system. The machine translation model, we had a blue metric of 42.8 compared to the 24 that is quoted in the state-of-the-art literature. So these were our results. Next slide. Yes, the future work from what we've done is to do end-to-end training where we can integrate the three parts into the global performance model. Also data collection, because we are lacking data for evaluating an end-to-end system for Yoruba. Yeah, so one of the challenges that we actually came up on is that we realized that the empty transformer model has the potential to work on auto damage restoration module because it only works on our artificial data set that we created. It doesn't perform well on the STT model. So we think that if we can get an error data set from the STT and use that to train our automatic diacritic restoration module, we can position to improve on it. And then we can have a performing end-to-end dialogue system. Thank you very much.
Questions?
I have a question about your damage restoration system. Could you explain a little bit what are the inputs, the outputs, and the nature of the network to do that?
So here what we get is that we just get that the transcript. So the transcript has kind of some words and sentences where they have errors, diacritics have been removed. So what this error and diacritic restoration module does is to try and restore the diacritics in the sentences, because this literature has shown that machine translation models can give you better results if you have diacritics in the transcripts. So, and also the other is that the output from the transcript has some kind of errors. So with this error and diacritic restoration, we try to improve on the transcript to reduce on the errors, which will be as a result of quite a number of things with the poor performance of the STT model. Yes. So what we did here was just to train a transformer model to assist in this task of the diacritic restoration.
And what data you use to train? The same data you use to, I mean, you need transcription errors, right? So
so what we did here was to get, we created an artificial data set, and what we did we created an error generator function whereby we inserted, deleted, and replaced randomly some characters in the sentences to remove the diacritics. So we created our own artificial data set for this because we knew that the output from the STT model is going to have some kind of errors as well. Yeah, so that is why we created that's why we created this artificial data set. So once we created this artificial data set, we kind of created the training and dev set and the test set. So we realized that we're able to actually decrease on the word error rate in the test set from 32% to 26.2%. Yeah, so this, though we kind of feel that if we're to have a better performing system, the solution would still be that we should use text from the text model to train the automatic diacritic restoration system. But unfortunately, it's with the time we have, and of course, it's not that easy to get this text at the moment. So we have to kind of find ways of experimenting around it.
I think you answered the question. Pedro looks very happy. Okay, let's thank the speaker again.
Hello everyone, I am Juan Pablo, and this is our team. Our mentor was Sugarcan, and I'm going to talk about our approach to performance-centered speech classification. Basically, this is for English, so basically to detect the accent of a given speech recording. So I will start with this question, which basically is, so what we have seen recently is that these large-scale different acoustic modeling has been kind of changing the paradigm on how to do or what to do with the research on ASR and also on other acoustic downstream tasks. However, like half of the presentation here has used way to way, for example, or whisper and so on. So the question is that is this kind of the beginning of the end of research in like a development, or what could be improved, or where should we head and start working on? So that's why we are targeting accent, because we have seen that, for example, recent research has shown that even when we do speech recognition on, for example, English, which is you can say the most available resource for ASR. For instance, this is just an example. We see that if we move to different accents, for example, to Malaysian, there is around 50% relative rate increase, which is quite dramatic, which is quite a lot. So one way we wanted to approach this is how we can embed this accent information into the system. So what normally the traditional setup we have, and for example, Whisper and all these models, is that you have a bunch of audio data and whatever language, let's say English, then you train your ASR system and then you use it in different. So, but what we have done here is first, we wanted to create an accent classifier. So basically, this accent classifier can be then later used for example, a downstream task, or for example, train an accent aware ASR. We didn't train any ASR system. We just focus on this and how to develop as much as possible. This also, one of the main issues is that there is no open source data set with this or any open source model. So that's kind of the first of its kind of research, I would say, like in open source related. So what we use is the Convoy 3.0, which has 16 obtained 16 accents from the portion of the set that is in English. These are the generalities, and we have accents for all of these different countries and so on. So our recipe is entirely developing a speech brain, and it's based on the common language recipe, but it's with accents. So basically, instead of doing language ID or language identification, we do accent identification. We use the ECAPA-TDNN model, which is, so we use a model fine-tune which is in a speaker recognition with box select, and also we train from scratch to have a comparison. We trained for around 20 epochs, and it took around 2 days in one RTX 3090 GPU. So this is more or less a global overview. We start with the data selection, then we do a model selection, which is the ECAPA-TDNN model. Then we obtain some metrics, and then we perform some analysis. I would like to focus more on this part, which is quite interesting, and will be good if you grasp the general idea. So these are the training results that we got for accent classification. So if we train the model from scratch, we just take it, start training, flat start training, we got around 82% accuracy. So if we actually take the pre-trained model, we go to 85, and if we use this pre-trained model, but we do some documentation, we reach 87% accuracy, which is basically one of the first, I would say, models that is targeting accent classification. So this is very interesting as well. This is a confusion matrix of the accent that we have, and as you can see, obviously the one that was producing more like the confusion was English from England, also from US, because it's kind of the high resource language, high resource accent that we have. So, but if you see on the other accents, actually it's quite interesting that in most of them is working pretty well. So those accents is the number of samples that we have, and of course the higher the numbers in the diagonal, the system So, and also we did some analysis of doing some SDSM to show how the level of clustering between these accents, and it's quite interesting to see these phonological similar accents. For example, Australia, New Zealand. Also, if you go to Canada, US, you have some similarity there as well. And if you go India, Malaysia, there is also some similarity that you can see. And for example, this is also quite interesting to see Organ Way similar. And all these countries have some kind of similarity in this also. We saw some misclassification, for example, also England, Wales, and US, Canada, which are more closer in this space. So as a conclusion, so we classified with this. We developed this model. We started a bit before the hackathon started, but basically we developed everything. We developed the recipe, we open source it. We also developed, we also got this database or pre-processed this database from Common Voice, and also open source it, and we trained these 3 systems. So also we found these like the levels of the misclassification. We show that as a future work, we like to start on the ESR side, and maybe end with a conference paper about how to integrate this in the ESR framework. So, for example, how to improve ESR, do some contextual biasing or accent-aware language modeling when you first detect the accent, and then you can swap the language model while doing decoding and so on. There are many things that can be done. Or, for example, what is in NLP going on, like the adaptation. So, yeah. And these are you can find the GitHub repository open source there, and that's the demo in coding phase, so you can access and check yourself how it works. You can record yourself and see which accent is closer to your
Thank you. I think we have time for one question, quite honestly. Because we are falling behind a little bit.
Yeah.
You mentioned augmentation.
Yeah.
What do you do for augmentation?
So we add some noise, some noise augmentation. Basically, we use a database for doing just augmentation on top of that. We were running, we didn't have that much time. It takes around 2 days to train. So we just wanted to get something out of the box, but the performance would increase easily by doing more augmentation, spec out, or something like that. And so on. And I think also this would be very interesting when you have a lot of, let's say that you have a lot of data and you want to sample from that data to create a more, I don't know, like a system that works well in different accents, like a pre-training, the pre-training phase. Also could be also something, for example, with gender, like as you want to include all these variables into the process of pre-training.
Okay, let's thank again.
No, there was
a follow-up question?
No, just if you want to spell out the novelty of this work.
The novelty is that one. The first thing is that there is not any open source that I am aware of any system or model to do accent recognition in English. So if there is nothing even in English, there is nothing in other languages. So the second novelty is that we are releasing all the training scripts, inference scripts. So basically, you can take all the languages in Common Voice, and if they have the data, you can do this for other languages very easily. So I think most of the novelty is the open source part that is now free for everyone to use.
Question. Okay, thank you.
Right. Hi everyone. My name is Olga Kalenka, and today I'll present you our joint work as your resource approach for code-switching text generation and filtering for automatic speech recognition. So the problem that we are trying to tackle here is the following. There is little textual data available for training satisfactory language models for code-switching ASR systems. And the problem here also is that automatic code-switching text generation systems do not take into account some of the prior linguistic knowledge, which can be visualized. So the solution here is to first build such a system that can generate arbitrary code switching data using constrained beam search decoding within a neural-machine translation system, and which is trained with parallel data. And after that, we can use this generated code switch data, and we can automatically select and filter it by using the linguistic knowledge and select the data which seem as most natural code switching examples. So first of all, for the arbitrary code switching text generation, a transformer encoder decoder translation system was trained with the following triplets, so X and Y for the training examples and predicting or Y or X. And the constrained beam search was applied on the output, but also the input examples were masked as well for this system to work as a neural-machine translation system. And using this constrained beam search approach, arbitrary code switching examples can be generated by masking the output at some points at any time.
Something.
Secondly, once we have the generated textual data, we can filter the data that we achieve. And, well, oh, this is the second slide. Okay. The first idea for that is that there is a matrix language that defines the grammar of the code switching utterance. By using this idea, we can implement such a system that uses pre-trained neural-machine translation system for English and Mandarin, and vice versa, to generate monolingual utterances, which can later be rescored using monolingual language models. Then, using that, we can compare the scores on the language models to retrieve the knowledge about how much this utterance corresponds to one language or not. Secondly, the second idea that we see in linguistics is that some words and word categories tend to switch more. So once we know the matrix language, we can then analyze the words that have been interchanged and to which, first of all, which part of speech tags they belong to, which dependency tokens they belong to, and also what are the connections between the translation and the original monolingual utterance. So first of all, I would like to look into not the accuracy, but the recall of the system. So how much utterances of the data sets the systems has labeled as true, as yes, this is a code switching example. So the interesting thing we can see here is that for the original CMA data, it doesn't perform very well. Ideally, we would want this to be 100. But here, of course, this is some ideal that we would like to reach someday. The interesting thing here we can see, though, is that when we train a generation system that is pre-trained on real code switching examples, it performs extremely well. This is due to the fact that a generation system trains to generate such utterances so that it learns the grammatical patterns, the grammatical categories in which the insertions occur. And well, the Gale corpus stands somewhat in between these results. And for the actual accuracy, we can see that for the synthetic Gale data set, the system performs the best. And as a matter of fact, it is able to filter out as much as 50% of bad code switching utterances, which is very good in the zero resource scenario. But also, what we can discuss here as well is that for Gale, the score is bigger than for CME, the synthetic CME dataset, and the real CME dataset. This is due to the fact that Gale dataset is more regular and the transcriptions are better aligned because they are human generated. So this is it for the presentation. And I would like to show you the demo. So for the demo, I'll just show you this example. How it runs, since we have a new presentation. Oh.
That can help.
Let's see. Wow, yeah, please do. This turned out to be more difficult than, okay, there's the message box. This is the Telegram. Yeah. So it welcomes us, and we enter our position example. It will think for some time, and then give the result that the matrix language is here estimated and is Mandarin. And also it tells us what are the results from both of the models. This is something that you can play around as well. Thank you for your attention, and I'll be happy to answer your questions. Questions from the teachers? Or maybe some things that are not clear enough, I can explain.
Could you go back to slide 5?
Yeah.
So so you say this is zero shot, so you're not training with code switch data at all?
Yes.
And I guess here you start with.
This is not a training pipeline. This is more like an inference.
Inference, right? And
yes.
you're scoring the translation with a regular language model to know whether it's a good translation.
Translation. It is. We haven't calculated the metrics for it.
Yeah.
Visual analysis, mostly the translation system as well. It tends to go a bit crazy with parts, when it tries to translate parts of utterance, but on average, it's fine.
Yeah, I guess what I didn't understand is how do you generate the inference system? How do you generate the code switch synthetic data?
Code switch synthetic data is the previous slide. Yeah. So this is being generated in the following way. So this is a training pipeline. On the other hand, the way this is launched on inference, an utterance, for example, of Mandarin as X is being input to a computer. This part would be masked for the inference, and our output here would also be masked, but not the whole thing. At some parts, it would be masked out. So, and the places where the word would be masked out is set by the user. So it's not like it's chosen by some kind of smart system of code switching prediction. This is why we need the filtering system, because it is able to filter out if that was actually a good selection of a code switching story.
Okay, thank you.
Okay.
Okay, hi everyone. We are team district, stands for Selectability Transcription in Indian languages. So for our team, we have Srinivas, Meg, Somi, and Madhina along with our mentor, short-term doing some range. And this is Saurabh, and I'm Shafi. And our project is mainly going to be on, speech recognition with the results of multiple dialects, and large-scale speech recognition models in Bengali and Bhojpuri languages. Okay. So, looking at the motivation, we consider India, which has the huge population but low literacy rate.
and also high adaptivity of digital technology. These combinations kind of make it ideal for voice-human interfaces to be integrated into products, right? So that it can be used to the masses. But the main issue, to actually do this is the language diversity of India. First of all, there are so many languages, and each of these languages has so many dialects. And we can kind of consider the dialects in India as being region specific. As go from region to region, a lot of things keep changing, the speaking style, the vocabulary, etc. So these things, kind of make it a challenge for this speech recognition. So how do you even, kind of handle speech recognition in such a diverse landscape? So in this slide, we have mainly just showcased few languages. Making to know is the Bhojpuri and the Bengali one that we'll be using as in our project. So the first thing when you want to build this speech recognition is to actually have data sets of these multiple languages, right? So when you look at many of these languages, actually don't even have a proper ASR data set. Forget about dialectal data set, right? So that is one thing to actually have the data to do the modeling part. And so for that, that's where the recipe project comes in from Indian of Science along with NANATech, and it's been funded by the Bill Gates Foundation. And so we are really using the Bhojpuri and Bengali data collected as part of this project. And we have 5 dialects for Bengali and 3 dialects for Bhojpuri. And in total, we have around 1,200 hours for Bengali and 1,000 hours for Bhojpuri. So these are mainly the stats from the previous slide. And we need to showcase that the speakers, the utterances, things like that are balanced into different dialects. Okay, so before we go into what we have trained, first of all, let's look at the performance on the existing model, pre-trained model. So first of all, for Bhojpuri, we actually use the Hindi pre-trained models because there's no Bhojpuri ASR as well. So we have the Google Cloud ASR, then we have Whisper, we have Vakya, so different models, and also the same thing has been done for Bengali as well. So we can see that across all these models, the best WR is close to 40, right? So there's a lot of work to be done to actually bring down the error rates for dialectal speech. Okay, so what are we doing and what's our approach? So first of all, we kind of want to, we wanted to look at it from different approaches, different toolkits, different learning methods. With all of this, we need to figure out, is there a particular way of learning that could aid, like a multi-dialect data set. So towards that, we all use like different methods to train these models. So looking at the culture style models, we have the TDNN, and which relies on the phonetic lexicon we have for the entire corpus, and we have results for that for Bengali and Bhojpuri. And then we have ES unit models. So even here, we tried a lot of different configurations, and finally we ended up with a custom implementation, which kind of uses like a multiple encoder followed by scoring function. And with this, we got the best performance for the Bengali. And again, we tried, XLSR fine tuning with Hugging Face code base. And finally, let me move this. Okay. So finally, we got the best performance for Bhojpuri with the Nivo model based on conformal RNP. Okay. So apart from that, we also did a lot of different ablation studies, mainly to understand the variability between these dialects. So we know we kind of like train dialect-specific models and decoded in particular configurations, mainly to understand the performance across dialects and what you need to actually get good performance all these dialects. And the same experiments are repeated on Bhojpuri as well. So these are mainly some of the experiments that we have tried, and we did try a lot more configurations, and all the other results are on our website. So now, Saurabh will mainly talk about how these models can actually put to use in public so that it can be usable by the general population.
So consider an example of Lakshmi. She is a semi-literate woman from a remote location in India, and she can fluently speak her mother tongue Bengali, and she basically represents a significant part of Indian population who has access to smartphone and technology, and they use voice messages on a regular basis on social media platforms such as WhatsApp. But they still travel to bank for like 40 to 45 minutes and stand there in long queue just to get something as basic information as like knowing their account balance or printing bank statement. So with access to a reliable speech technology in their mother tongue, they could easily interact with their voice on a digital platform and get those information in a much less time. To demonstrate that example, we created a WhatsApp board and a demo of which will be played here.
Here is a demo of using Bengali WhatsApp system. You can reach the screen by scanning the QR. টমেটো চারা কোথায় পাবো? It recognizes both correctly. Now I'm going to try few banking domain sentences. স্বাস্থ্য বীমার কি কি সুবিধা আছে? কন্যাশ্রী পেতে গেলে কি কি করতে হবে?
So this board was created using one of the
আমাকে মাসে কত টাকা করে দিতে হবে?
Other than that, we also, for a more real-time application, we have also tried implementing a streaming ESR model. For that, we use NVIDIA Nemo framework, and for that, we also have a demo.
আমার বাবা একটা কথা বলতেন, আমি ঠিক পুরোটা মনে করতে পারছি না, একটা কথা আছে, শরীর এমন একটা জিনিস যা শোয়াবে তাই সয়। আর আমি মনে করি সচিন তেন্ডুলকার শরীরের নাম মহাশয় যা সয়, হ্যাঁ শরীরের নাম মহাশয় যা শোয়াবে তাই সয়। সচিন তেন্ডুলকার এমনই একটা মানুষ, সে এক্সেপশনাল না হলে এই
So that was it for the demos. So for all our experiments and all the demos, and if you want to try to observe, do go to our website. And also, if you're interested in the data set and the models, we'll be listening in the next 2 minutes. We're open to any questions. Thank you.
So, questions from the judges? So what were the specific challenges in this project?
Well, one thing is, of course, it's a large data set, and we kind of have to deal with what sort of experiments we actually want to run. And also, kind of coordinating between all the team members, kind of what models we want to try, etc. But apart from that, also, after we did the baseline, we were trying to figure out, what are some of the extensions we can do, which could work well for, dialect scenarios. And we started experimenting with multi-dialect, multi-encoded scenarios, and different contributions of that, and some of those work really.
Also, studying the data was like one of the most important challenge, because the entire data has been like crowdsourced. So knowing that what are the problem there in the data set, like some kind of noise, because it was recorded using different devices. So understanding each part of the data was challenging.
Okay, we can continue, I guess. Thank you.
Thanks for speaking again. We are a little bit behind.
Good evening, everyone. We'll be presenting our work. We are titled as Shravan. We are trying to build multilingual ASR for Indian languages. We have been mentored by Brian Yang, and our team consists of Ashish, Moses, Arun, Shravan, Vrinda, and myself, Vasishtha. So we have heard earlier in the presentations about the diversity of the multiple Indian languages in India. It's dominated by a few languages, but there are many languages which have few text support also. So there are about 120 known languages, and there are about 1,000 languages which do not have a script in India. So these are the types of languages that we're dealing with in our country. And the word Shravan by itself means to listen. The whole purpose of an ASR system is to listen and capture what is being said by the speaker. And we are trying to develop systems that do that in an efficient manner. So the motivation is, though we are using energy to build models, finally they need to be put to use in a proper manner. So we are trying to look at applications which impact education, healthcare, customer care, and all sorts of entertainment purposes. So as a part of this work, we have tried to develop a system which does speech-to-speech translation or video-to-video translation, so as to help a speaker from one particular Indian language to communicate with another. For example, the two of us standing on the stage speak two different Indian languages, and we usually go to English as a common term to communicate with each other. So this is a speech-to-speech pipeline we have built a demo for. So we start with the speaker speaking in a particular language. We have built ASR models on ESPNet with the conformer framework, a data-to-bit model pre-trained on about 12,000 hours of Indian unlabeled data, and we have fine-tuned the whispered models of all different configurations, tiny to large V2, over about 6 different Indian languages. So once the speaker speaks in a particular language, we have a spoken language ID model which we have fine-tuned towards the 6 Indian languages, and that predicts the language. But in this case, let's say it was English. We had Indian English data as well. Let's say it was predicting English. Then the corresponding ASR system would be doing the inference on the particular language. And post that, before we go to our translation module, machine translation, we need to take care of a few things. Things like inserting punctuations in the right place. For example, if you see the sentence without the punctuation in the right place, it could be input in a completely different context. So we have used the punctuation module from Vakyansh. It's called index punct. And also we have a language ID model in place to get the exact machine translation model to be used in this particular use case. And after the punctuations have been inserted, we are using the models from SMT lab at IIT Madras to generate back the speech from text. So the different data sets we have used to build the different ASR models, the ESPNet models, the data models, and the whisper fine tuning. These are the different ASR data sets that we have used for different languages. And the results we have gotten during this about 1 month of fine-tuning the whisper models, we have done exceedingly well competing with systems from Google and Microsoft, the whisper fine-tuning model, and we can compare it with the standard whisper decoding. For instance, if you don't do anything on whisper, the multilingual whisper model, and directly decode on the Gujarati data, the test sets we have used, the Google Plus test set, it gives about over 100 WER, but once we fine-tune, we have come down to about 27 WER, and that is the small whisper model. We have also having models of different configurations. The results presented over here are the whisper small fine-tuning. Then the similar results we can notice for Kannada, Tamil, and Telugu as well. Now, we have open sourced all of our models, and we see them being used regularly. This is over the last 10 days, and we see significant interest among the Indian community. So the different challenges we have faced in developing the systems, the Indian languages especially, WR might not be the best of metrics to go for, because a particular word can be split into two different words. For example, in this case, Mitra Potu Undaga, that's a two Telugu words put separately, but they can be clubbed together, and if we compute a WR, we'll get a error. The error rate would definitely increase. So that is one issue which needs to be taken care of. And similar to English, the punctuation errors, the data set needs to be robust to include different kinds of punctuations in the basically mark proper punctuations. So as a part of our future work, given this entire setup, we are moving from ASR to machine translation and back from machine translation to TTS. So probably we can try to reduce the number of models involved, because any error in a particular place would get cascaded and it will affect the final TTS. For example, if there is an error in ASR, that would impact the machine translation, and that would indirectly impact the text-to-speech model performance. So we are planning to basically build speech-to-text models which go from one language to another, and then probably from there a few diffusion models we are planning to try out to go from text to speech. So Brinda will now be demoing our video-to-video module. So we choose the source audio language. For now it's English. Fine-tune is the basic whisper model which is available. And for translation we are using the LLSB models from Meta.
Hello, we are working on Indian languages. We hope this will work. This will benefit for the Indian society.
each of the systems will work one after another. The ASR companies first feeds the input to machine translation.
नमस्ते, हम भारतीय भाषाओं पर काम कर रहे हैं। हमें उम्मीद है कि इससे भारतीय समाज को फायदा होगा।
So basically, once we perform bad on the source audio, we use those timestamps to stitch back the audio. Basically, we have the web PTT, the source web PTT. We use the same timestamps to stitch back it into the target video. Basically, we are doing a simple video interpolation to do the job. We are done with the demo. We also have two other demos, one for speech to speech and another for just going from ASR to machine translation. That's available for languages like Arabic or whatever NLP supports. Any questions? Yeah, please feel free to type.
Yeah, question from the captions.
So the video to video, is there another system that can do this?
Not that we are aware of, but we are trying to develop a better version of the same. I mean, here on the website, because we have a time constraint, the user won't be interested in staying for more than 30 seconds or so. So we need to do a basic interpolation in this case. But when we have time, let's say the user submits a video and has about 30 minutes to get back another video. We are having a system which involves some QCRI-based segmentation and hybrid segmentation and stuff like that, so that the quality improves basically. So that's a different interpretation system, but that we are still working on.
Okay, thank you, Ken.
Assalamualaikum and good evening, everyone. Our project is about Arabic dialect identification and diarization using Wave2Back 2.0. Our group is made up of myself, Daniel, from AI, Phoebe from University College of Dublin, who unfortunately couldn't make it to Qatar because of funding issues, and Yasin from QCRI, and Yusuf also from AI. We have been mentored by Dr. Marcus Miller from Amazon Alexa. So the Arabic language is spoken by over 300 million people across the Middle East and North Africa. It consists of 17 main dialects, and these dialects have similar vocabulary and grammar, but differ significantly in terms of pronunciation, colloquial expressions, and cultural references. And this makes multi-dialect Arabic ASR a super hard task. And this is why
just click it.
Yeah.
Sorry about that.
So this is why for the hackathon, we decided to train a model for dialect identification or diarization. Because dialect identification helps in improving the accuracy of the ASR model, because we can tailor its transcription to the specific dialect being spoken. Also, we can enhance the robustness of the system, because it can better handle variations in pronunciation, vocabulary, and grammar that may be present in different dialects, so we can accept a wider variety of inputs. And finally, it increases the efficiency of the ASL system, because we can use more specialized models or better processing techniques, which will lead to faster decoding. Some of the social and economic impacts of our project is facilitate communication and understanding among people from different Arab regions who speak different dialects. Secondly, facilitate trade, education, and other forms of social and economic exchange. Thirdly, foster greater cultural awareness and appreciation, and can help to build stronger social and economic ties between different Arab regions and communities. And finally, it can help to preserve linguistic diversity within the Arab world.
Okay, so now let's move to
control
command.
Right.
Yeah. So now let's move to the technical part. So the first question, we try to fine-tune whisper. So why fine-tuning whisper? Actually, we read many papers about like Arabic dialect identification, and a lot of work has been done like with Arabic dialect identification, but they all revolve around like study the features, which features, what are the important features like in the Arabic dialect identification, and then they build on the top of this feature a big DNN model. But we can make use of this way today because it has been trained on like a lot of data, and it's already like learned like the context of the audio, learns a lot of speech aspects, so we can make use of this instead of retraining from the beginning. So here we pass to see like the architecture of the model. Let's start with the data. We work with like an available data, which is API, which supports like 50 hours of 15 hours of dialect in Arabic, 10 hours per 5 dialects, and we got wait to make its RTR from trained on Arabic ASR. We freeze like the first layers of feature extraction, and basically we adjust like a small DNN to fine tune it from this stuff. Compared to actually first we faced like another fitting problem, and to backup this problem we tried, instead of having like a chunk audio, a fixed size of audio, we tried to have like different durations of chunk size from 1 second to 9 seconds, and we tried to do a lot of data condition techniques, adding nodes, and also like perturbation of the original dataset by speed, by like changing the speed of the audio, make it like faster or slower. Basically, our proposed model, we got 61.7 like as a reference, which is like good compared to like state-of-the-art papers. We have like this paper which was like the state-of-the-art in 2018 using IELTS with ACM, and this paper like using MFCC and the CM and ACM got 65.5. But we think that we can make it better if we train it on like much more equals, because the duration of our time is just 2 days, so we couldn't make like much better results.
So after we finished the hackathon and training the models, we came out with several stuff. Firstly, I showed the notebook tutorial, that then users can use as a base to modify for other classification tasks on top of this model. Secondly, since we were exploring and targeting a streaming service where we diarize the dialects as the speaker goes, the system can be modified and tweaked to accept longer audios that they can be used to annotate videos, for example, or stuff. Thirdly, the model will be uploaded to Hugging Face so that it can serve as a base model for future ASR models. And yeah, and now the demo. So first, to explain the demo, as you can see, this is the current prediction of the last chunk, and these are the history of predictions. So we had 5 classes: Egyptian, Gulf, Mediterranean, MC, and North. And you can see that on the left, it's just the code running, and then on the right, that's it.
كل شباب من شباب الالتراس، حتى بتتقال كافيه او كشعار. مره واحد راح يشجع مات.
ما حدث كان مؤامره.
ثبت انه النظام يعني اسرائيل ضربته في المواقع بلواء 90
The Clinic أصبحت وسيلة إعلامية تثري النقاش العام وتثير القضايا الساخنة. إنها تستطيع ترتيب أولويات
حليبوا بلي فيديو انسوليت اللي نتوما راكم تبعتوهم لنا عبر الفيسبوك.
After the user finishes, they can download the predictions and then they can use it to diarize build over for an ASR model to then use a different model for each of the predictions according to the. Thank you so much.
Questions from the judges?
Okay, let's thank the speakers again.
Okay, without further ado, let's get started. So I'm Bokan, with me is Goku, and Akash will be joining us virtually in Canada. And I'm presenting to you Autodub, which is a video dubbing platform that we have developed. And so, first of all, what motivated us to make this video dubbing platform? Well, we noticed that most content online, especially videos or educational videos, are actually in English. However, if you check over here, the majority of the world is not an English native speaker. For example, in Chinese, only 1.4% of the top online content is in Chinese, whereas it consists of 14% of the world's population. So we realized that if we were able to get all these videos in the native language of the users, well, this will create a lot of opportunities, not just for education, but also for cultural exchange and the like. The existing traditional solution for this is human dubbing, where you have humans to dub it, but that's expensive. We also did find some online products to do this, for example, Dubbers. However, these end-to-end AI solutions do suffer from some drawbacks. For example, they suffer from accuracy impairments, especially if they're silent, where they go from one component to the next. There's also time synchronization and some style problems, but I will get to that in a second. All right. So, introducing Autodub. Here, we developed a platform that not only allows us to use all of the state-of-the-art components for video dubbing, which is transcription, speech-to-text, translation, text to the other language, voiceover, and an additional feature we developed. But we also integrated this with a UI that allows humans to be in the loop, which assists in the AI process. At the current moment, we support these languages, but it is definitely extensible. So, Goku will do a demo of this, but basically the gist of it is the user uploads a video, generates a transcription, they can make edits to it, then they can translate it, and also make some edits to this if they would like to. They can do a voiceover, do the matching of the voiceover to the video, and to make adjustments to it, and finally export it, which we will get to in a sec. So, what are the unique features versus what is on the market? Well, we looked at a lot of products on the market, and what we offer is the ability to showcase all of the cutting-edge models that is available. Actually, even today at the conference, we noticed there was a cutting-edge model for Whisper that was trained on Indic languages, which is very interesting and something we could even integrate into this platform. All right. So the main selling point is the human-in-the-loop design because of the error cascade. As in the ASR's error will cascade to the machine translation and the text-to-speech. By using human in the loop, the human is able to edit this the synchronization of the generated speech to the video that will suit them, and it will greatly speed up the translation process. We also, in addition, we noticed that the online services do not offer background audio separation, as in the final product only has the text-to-speech voice. It doesn't contain the original sound effects, music of the video. So we adapted a model, which I'll get to in a second. Try to be quick. Some technologies we use. So for transcription API, first of all, for English, we just chose the best OpenAI's Whisper ASR. However, it is actually possible to fine-tune it for Arabic and Indian languages, as we have seen, which is really cool. And for fallback, we have also applied GCP. The same for translation, we use Metas and NLB, and for English to any other language, which we found to perform the best, and for every other else, we can take the next best model. For our voiceover API, actually, this is a custom-built one by Google for the Indian languages. He trained the state-of-the-art text-to-speech system on 13 low-resource Indian languages, which is immediately applicable. This is where we thought that most of the video content could be localized in these regions currently. And as a fallback, we have other features. And we also came up with a technique because of this sound effect and the fact that, you know, there's no ECAPA sound and there's no original background and sound effects. So we adapted a model trained on music instrument separation. We found that this actually works empirically quite well for extracting all the non-vocal sounds. So we just did a concatenation of that, and we used that to reapply it at the end of the pipeline, the timeline. Yeah, so in summary, you know, if this becomes a real thing and this takes over, we can greatly increase educational accessibility for many of the non-English speakers, also improve the accessibility of content creators and economic opportunities, because we hope to also integrate humans as voice dubbers and collect data and use this to train data for the entire speech ecosystem. So yeah, takeaways, and we'll just get to the demo for the sake of time. Yeah.
So I'll give a quick demo. So this is the informational video about Abu Dhabi. So I already ran a transcript. So the user just has to create our account in our website, which is autodub.io. We ended up like deploying it in Google Cloud Platform. So you just have to create an account, upload a video, and click the transcribe button. Boom, you'll get the transcript. And user will also have the option to import the subtitles. So for some videos, people might have the SRT files already available. So they could use it, replace the subtitles if they already have it. Then, so right now we support these languages. Let's do Arabic translation.
Maybe even play it before that.
Yeah. So
Abu Dhabi. I will go to play for this.
So translation is very fast. So we actually batch the translation, so it is like running instantly. So then the user has to click voiceover. So now it is producing like it is synthesizing speech for every subtitle. But the problem with this is it usually doesn't synchronize with the source language. So the usual most of the existing approaches, they do like frame level video interpolation, but that is not a good idea because like it expands the video. You need to have every single copy for every new language that you operate on. Not only that, sometimes when you adjust the frame rate dynamically, it affects the video quality. So that's why we want to do it how it's done in the movie industry, like the manual, like instead of doing the actual translation, we want humans to do the translation that may be less accurate, but it's time constrained. So here we guide the users through this platform to say like which subtitles are very fast. For example, this is very fast. The user can edit it. So I don't know Arabic, I'm just learning Arabic, so I'm just removing the text, but the right way to do it is like rephrase it in a throttle. So they can rephrase it and regenerate.
It's color-coded in that way,
yeah.
So you know the level of speed that you should try to match.
So now it is, now it came back to normal. So now this is very slow. So it's not only like this platform, like we not only support the content edit, but also the timeline edit. For example, here I could like shorten the time. And regenerate. Now it came back to normal. So the process is like you have to do all these, bring all the subtitles to normal and click voiceover again. So now the final video will be this, will be like speech, like the speed will also be consistent throughout the video. That's it. And also one more thing is like if you play the final audio, you could also observe the non-vocals from the source video getting translated here. So this synthesized speech is not monotonous. The background, not the non-vocals, are like transferred from the source video to here. So these are fast because like we have to edit it.
دعنا نلقي نظرة على خريطة أبو ظبي ومن الواضح على الفور أن أبو ظبي ليست مجرد مكان واحد.
That's it. Thank you. Okay.
So
what more do you think you can do to make this deployable? You said that if this takes over, it will.
Oh yes, there's a yeah. Okay, yeah. So one easy thing is speaker embeddings. So we're planning actually, because we don't want this to be purely AI. We also want to adapt like the human elements. So we want for the text to speech to also have the ability to actually have native dubbers. And so we have speaker embeddings that could match these two, I guess, speaker profiles. So if you're a video artist and you're trying to dub your video, you could try and match your voice directly to somebody that sounds similar. And if you have like thousands, for example, you don't have to like listen through all of them. You just find the best match.
Yeah, and we also we already have this API implemented for using the speaker embedding from Pioneer, so you can access it in this API talk. So it automatically does. The good thing is it does it in a cross-lingual way. Even though the source and like target are in different languages, it matches the speakers based on the metadata, based on gender and like nationality, all these kind of metadata.
Yeah, a lot of the APIs we have, we just haven't had time to integrate into the UI, which we're hoping to do as we keep working on it, hopefully.
Thank you. Okay, next thing.
Hello everyone, my name is Martha. Today I'm going to present Commentator voice synthesizer with my teammates Fabian, Hubert, and Lisa, mentored by Professor Kim. So first of all, according to a high growth in the gaming industry, there is projected in 2023 that the revenue would reach $221 billion. And there's a problem actually that audio engineers and studios are finding huge problems. For example, in creating voice and like synthesizing voices, so they have to create like over 1K of speech variations, and they end up, for example, in wasting a lot of time, money, and effort. So for that, we came up with a solution to create a speech generator for a football commentator in order to make the video game more engaging. And also, we are going to generate the noise and the crowd with the speaker. So actually, the project pipeline, the first component, we collected the data from YouTube. We crawled the voice of a very famous commentator. His name is Shravan. He's a Tunisian. So we have the data without transcriptions. So we already have an Arabic pre-trained ASR model. We transcribed the speech using this pre-trained ASR model, and then we segmented the data using voice analysis detection, and we just took the best speech samples. After getting those samples, we had to segment also the speech again manually to 3 different classes: excited, neutral, and very excited. And then in order to get a better alignment, we applied CTC segmentation. And then we built a text-to-speech model using grids. We fine-tuned it on our data set, which actually reached only 15 minutes, like 3 examples. And now I will show you 2 videos. One of them is generated, and the other one is the real one. And I would like you to guess which video is the generated one. So, the next one.
خطيرة وكرة ممكنة ورصديدة ممتازة. ممكنية ثانية ويمشي ورصديدة. ميسي وعليك خاصة تعرف فرحهم شي كامل يلعب شي.
And the second one, let's see.
خطيرة وكرة ممكنة ورصديدة ممتازة. ممكنية ثانية ويمشي ورصديدة. بمسي وعليك خاصة تعرف فرحهم شيل الكرة ملعوبة الثالث الحارس يمشي بابي خطيرة شيل يا طويل العمر شيل يا طويل العمر شيل البطولة شيل البطولة شيل.
So actually, which one is the right one?
Wow.
Can you guess?
First, second one is
Most part generated.
yeah.
Actually, the second one is the real one. Yeah, and the first one is the yeah. Okay. So actually, we built a model like in 2 days, but we worked on labeling the data before. Yeah. So the challenge is actually. Okay, so our challenges, the main challenge is that we have a lot of noisy data and music background. Also, the annotating the data is very, very demanding task. So like annotating according to the excitement, it's really hard. And also the transcription is inconsistent because the person is like Tunisian, he speaks like some of French words and the names of the players. So we had actually to manually change a couple of words. So that said, we ended up only in like 157 minutes. And thank you for listening.
I have a question about the annotations. So this is a text-to-speech, so you have to annotate the transcription, but you also have to control emphasis, energy. How do you do that? Did you use extra labels or extra parameters that go to the TTS? Or?
No, actually, in the future, we're planning to do like multi-speaker in a way like to have multi-labels. But now what we did actually, we just fed the data. But we had, for example, the segment that is like very excited, is like very excited, with no segment after it like only excited or neutral. So, but the thing is...
So more like HTML tags in the transcription, like excitement, like bracket, excitement, text, close excitement, or something like that?
No, well, like for feeding the text, we just fed without any labels.
I see.
Yeah. But you can see like from the demo, like from at the end, when he like when he raises his voice a lot, in the real one, he can really increase the pitch better, way better than ours.
So you're not really controlling yet?
No.
Okay.
Because we just had like 24 hours. Any more questions?
So how well would this modeling generalize in other parts of the game? You said that you have 3 classes: neutral, excited, and very excited.
Yeah. So in the future, we are planning, for example, to have the game, okay, and to have like for each one of them like a label. So you should like be able to feed the label and say, for example, that this is a goal, and say that this is in a very excited way, you know. So for example, now when we tested this goal, it was like goal, you know, not the same pitch. So the model for sure needs a lot of enhancement, and there's a lot of things to be done.
What can happen when the team lose? Your model is not going to do anything. It's always exciting.
And actually, by the way, there was a very huge correlation between the linguistics and the pitch. So for example, you can see the word tasdida, you know, it's always on a high pitch. So also there was a huge correlation that each time you say this or you will end up in a very like high pitch. Okay. Thank you.
Sorry.
Good evening, everyone. My name is Hawa. I started my master's in machine learning last 3 months at MCAI, but I hope to do my thesis in conversational AI. So my supervisor just said that I attended this hackathon, so that's why I'm here. I really don't know much about NLP. Yeah. So me and my team members, Nizar and Fatima joined today actually, and Nizar joined like 3 days ago. He's an high school student. So our topic is on speech-to-speech translation for Arabic dialects. So our motivation, the brain behind our idea is, okay, in the GCC countries, right, more than 50% of the workforce consists of non-native Arabic speakers. So we can speak Arabic, but I also can speak Arabic, but I can read and write. But if you want to learn Arabic to speak, you only learn the modern standard. So if you want to converse with a native Arabic speaker, it's a problem because they speak differently, and because you are even learning a language, it's hard to communicate. So that's why we have the idea of a way to translate from between Arabic dialect or from English to Arabic dialect or from English to modern standard Arabic. So the main objective is the translation, as I said, and also we hope to improve automatic speech recognition and machine translation for Arabic dialect while incorporating gender. Because for Arabic, you need to, the way we speak is different based on gender, so we have all of this in mind. So we have like a proposed system, so where you get the input speech and the dialect, you select the dialect that you want the output for, and we have like these 2 processing modules, which is the gender and dialect identification and translation generation. And from listening to some people speak like us, you already have the data set for translate data for Arabic dialect, and they have the dialect identification, and they have the accent which can be doing for gender identification. So I'm really happy at least I got that. So the novelty is there's no published work or tool, no public published work or tool or data for speech machine translation for Arabic dialects. And we hope to create a foundation for research and projects focused on integrating the gender into Arabic speech generation and translation. So the challenge is there's no data. The gender variation also in Arabic, I'm sure that's going to be a huge challenge how we must start it. And also the inconsistency in Arabic dialect, like some words, like you mentioned, means different things in different dialects. And also the limited time, we had like 2 days to work on this. So for now, what we did, the mobile-based interface, it was done by Nasser, the high school student. He built this app yesterday. It's not functional, all the audio, it's like hard-coded into it. But this one, it's just a simple web-based to change English text to modern standard Arabic. So in this, it's like a cascaded system for like ASR, then the text translation, then the text to speech. I used the Whisper and Google Translate and Google Text to Speech to make this. So the lessons we learned is there's limited speech resources for Arabic dialects. And yeah, the future work is to improve the current implementation to improve all the proposed models. And well, before we're thinking to create a data set, but now I think someone has a data set. And we also found ICST, it's a shared task. It's starting January 14, and they're going to release a data set for Tunisian Arabic dialect. Open to gender with Fatima, and we'll see you.
There might be a question.
Okay, does anyone have a question? No? No? Okay.
Let's thank the speaker again. Okay, hold on. That was the last one. Come on. No. Okay, so we had a lot of great teams, right?
Yeah, a lot of them. I want to thank each one of you guys. You did it very, very good. You rock it. I mean, since Friday that we arrived here, we were listening to all of your stories, right? Academic and non-academic, and it has been just very, very inspiring for us. We thought that we could show you some of our techniques, what we have learned over the years, but instead you brought us a lot of your knowledge to us as well. So we want to thank you very, very, very much. Okay, and for raising yourself. Okay?